All right, so today we're going to be looking at a process called nuclear decay. Nuclear decay is when we're essentially going to have elements of atoms that are going to actually change what the element is. So everything we've talked about so far have involved chemical reactions, changing bonds, changing ions, but the main element has always stayed the same. Carbon has always been carbon. And if you think back to it, what determined the element was the atomic number, kind of the small whole number on the periodic table. So you are going to need your tables for this one, your periodic tables. So the big one here, we used to write, like if we want to indicate what isotope of carbon or what mass of carbon we're working with, we would write its chemical symbol there, and then we would include the mass. And that was fine for what we were doing before, but it was just kind of knowing the mass and figuring out the number of neutrons it had. For nuclear decay reactions, we're going to write this somewhat differently. First thing we're going to do is, so we're going to say this is the old way, and this is going to be the new way. We're still going to write what the chemical symbol is. Carbon is still a capital C. Now at 14, the mass, that's still important. So we're going to write it right there. The other piece of information I'm going to need to include when I do these nuclear decay reactions is the atomic number. Since we are working with atoms that could possibly be changing element, knowing the number of protons, knowing what that atomic number is going to be really important and useful. So if you check your periodic tables, carbon has an atomic number of 6. I would say this even makes finding the number of neutrons a lot easier, because if 14 is the mass, that's the number of protons and neutrons. 6 of them are protons. 14 minus 6, we know that we have 8 neutrons there. All right, so this is kind of the new way that we're going to write isotopes and stuff. Really, we're going to go with the chemical symbol here. We're going to put the mass number on top here. And remember, the mass number will always be given to you, or you'll be given the number of protons and neutrons so that you can find it. And then this 6 here, this is the atomic number, otherwise known as the number of protons. And just to re-stress this, the atomic number, the number of protons, determines what that element is. So for now, for nuclear decay reactions, we've been looking at electrons essentially all year, really, except for maybe the first month. This time, we're not going to care about electrons much at all. Like, we don't care about how many shells, how many orbitals, how many outer shell. We're not going to worry about that at all here. All right. So that's kind of the basis for kind of how things are going to look here. Today, what we're going to look at are the 3 main types of radioactive decay. The 3 main types are indicated with Greek letters. So the 3 of them are, that funny looking fish thing here is alpha. We have alpha decay. We have this funny looking bee with a tail. That's beta. Those 2 are kind of easy. Alpha looks like a funny A. Beta looks like a funny B. And the last thing, if I go back for a second, funny looking Y guy, no real easy way to know this, but that's gamma. I believe that's a lowercase letter, but I might be wrong on that. All right, so what does this mean? So the 3 types of radioactive decay or nuclear decay really signify 3 different things that are being shot out of what are the nucleus we're looking at, what's getting shot out of it. So for instance, with alpha decay, we're losing what's called an alpha particle. What that really means, though, is we're losing a particle that has a mass of 4 and 2 protons. So really, it's a particle that's 2 protons and 2 neutrons. If you check, and if we still stick with masses on top, atomic numbers on the bottom, 2, an atomic number of 2 is an element on your periodic table. Really, the alpha particle looks just like helium. So if our parent nucleus undergoes alpha decay, we're shooting out this helium nucleus, this mass of 4, atomic number 2 nucleus. With beta decay, the particle that gets shot out, the beta particle, has a mass of 0, relatively speaking, compared to protons and neutrons, has a mass of 0. But it has an atomic number of -1. And really what's happening is, out of our nucleus full of protons and neutrons, one of the neutrons becomes a proton, and when it does so, it shoots out this electron. So really, another way to look at it is our mass isn't changing here, and our atomic number is actually going to increase by 1, but we'll get there. The gamma particle has no mass, has no charge, has no effect on the atomic number. Really, it's just shooting out energy. So we just signify it with another funny looking Y thing. Essentially, some atomic nuclei, they have too much energy. That's what's making them unstable. So to become stable, they just release energy. It's like they just let off some steam, and then they go down to having less energy. They're way more stable. They're not going to break down any further. All right, so these are the 3 main types of radioactive decay. Let's use these to actually predict what's going to happen to my carbon-14. So let's start off with, let me clear that. Let's start with our carbon-14. So we said it had a mass of 14, atomic number of 6. Let's say it undergoes alpha decay. All of our nuclear decay reactions are going to have 2 products in it that I need to figure out what they are. So if I'm writing nuclear decay reaction, I'm going to write down what am I starting with, what kind of decay reaction it is, and what are my 2 products. Now that first blank is going to come down to what was just up there. The first blank is over is what is that particle? So in this case, what is the alpha particle? I hope you wrote it down, because the alpha particle will be that 4-2 helium nucleus. So now, to figure out what that carbon becomes, I'm just going to subtract across. So my mass is going to go from where it's 14. I'm going to subtract 4 from it. So 14 minus 4, that gives me a mass of 10. Once again, I'm just subtracting across. So the top number, subtract 14 minus 4, 10. I'm going to do the same thing with my atomic number there. I'm just going to subtract across. So I'm starting with 6. I'm subtracting 2. 6 minus 2 should get me 4. And that's my atomic number. So now I need to go to my periodic table. I need to find elements with an atomic number of 4. And that should be beryllium. All right. So really with alpha decay, what we're finding is the mass numbers are going down by 4. The atomic numbers are going down by 2. Let's say my 14 carbon, my carbon-14 there, this time let's say it undergoes beta decay. All nuclear decay reactions are going to end up with 2 products here. So the first step is going to be writing down what that beta particle is. So what you should have written down before is that beta particle is a 0, -1 electron. Once again, that's just a proton, or a neutron, I should say. A neutron becomes a proton. And to solve this one, we still just subtract across. So 14 minus 0, 14 minus 0, because those are the 2 numbers on top, should give me 14. 6 minus -1. All right, so when you subtract a negative number, it's the same as adding a positive one. So 6 minus -1 is the same as saying 6 plus 1. That gets me 7. Go to the periodic table, and element number 7 is nitrogen. This typically is the nuclear decay reaction that carbon-14 does go through when it does decay. And it makes sense, the most common isotope for nitrogen is 14. Just to give you a little bit of extra knowledge there. All right. We need to go through one more nuclear decay reaction, that's that gamma. Let's start with carbon-14 undergoing gamma decay. And we're going to end up with Let me draw that line a little bit better. First step, the first blank is write down what the gamma particle is. That gamma particle is just a 0, 0 gamma. Essentially, it's a photon of high energy. And we're subtracting across. Luckily, we're subtracting 0 and 0. So 14 minus 0, 14. 6 minus 0 is 6. That looks exactly like this here. With gamma decay, we're not changing what the element is. We're just changing the energy state. Sometimes you'll see the carbon with like a symbol or something above it or next to it just to indicate it has high energy. All right. The cool thing about these three decays is it doesn't matter what element we're talking about, even if we're talking about something huge, something like borium-264. Borium-264. You might take a little bit of looking to find some of these bigger elements, but borium has an atomic number of 107. If it undergoes alpha decay, it works just like how that small carbon worked. The first box is still going to write down what that alpha particle is. So in this case, the alpha particle, 4,2 helium. Next step is just to subtract across. So 264 minus 4 is 260. 107 minus 2 is 105. With those numbers done, I can go to my periodic table, figure out what element 105 is, and it looks like it's dubnium. Db. The only tricky part is with the beta decay when you subtract a -1. It's the same as adding a +1. With that, there are some problems on Classroom to do, so go ahead and have fun with that. I'll be around if you need help.